Problem number 18. Show that this limit is equal to 0. How do we accomplish this? Well, for something like this, first off, note that if we plug in 0 in for x and y, we get 0 over 0. So, we can't just argue by continuity here. Instead, the best thing that we can do is to use the squeeze theorem here. So my personal preference is to use squeeze theorem in conjunction with polar coordinates. You don't have to use polar coordinates, but I think it allows us to keep track of things a little bit more easily. So x is equal to r cosine theta, y is equal to r sine theta here. And so we would end up with 5x squared minus 2y squared over square root of x squared plus y squared. This would equal, after substitution, 5r squared cosine squared theta minus 2r squared sine squared theta over square root of r squared cosine squared theta plus r squared sine squared theta. Of course, why do we do this? X squared plus y squared in polar coordinates is r squared. Take the square root of that to give us r. And so what do we end up with here? 5r cosine squared theta minus 2r sine squared theta. I'm going to factor out a factor of r here. Okay, so this is equal to this after the polar coordinate substitution. Now, to use squeeze theorem, we're going to slap absolute values on everything here. We need a lower bound on our squeeze theorem. 0 will work for that. And then an upper bound is going to be 7 times r. Let me explain how I come up with this. So the r just comes down here. And so our argument then is that absolute value of 5 cosine squared theta minus 2 sine squared theta, our argument is that this is less than or equal to 7. How do we proceed? We can use the triangle inequality here, that the absolute value of this is at most the absolute value of 5 cosine squared theta plus the absolute value of 2 sine squared theta. And so cosine squared theta is at most 1. Sine squared theta is at most 1. 5 plus 2 is equal to 7. Now, this is a way overestimate of how big this quantity can actually be, but that's fine. We just need some upper bound on it. And what do we conclude here? The limit as r goes to 0 of 0 is equal to 0. Limit as r goes to 0 of 7r is also 0. And so the limit as r goes to 0, 5x squared minus 2y squared over square root x squared plus y squared, after our change of variables, also must equal 0. And then if the limit of this expression with absolute value bars is equal to 0, the limit of this expression up here without the absolute value bars is also equal to 0. Okay, that is problem number 18. Now let's talk about problem number 19. This is another picture problem here. So the contour plot, we're given this contour plot here below. And so the first thing to look here is at this point A. This point A here. And realize that we have we have this kind of interesting intersecting contours here. And the fact that we have intersecting contours here tells us that, so this is 0, loops back, it's still a 0 on the back half of the loop. That's going to tell us two things. That's going to tell us that A is a critical point because the gradient of f of A is equal to 0 vector, and then further it will tell us that this is a saddle point. Why is it a critical point? Well, and I said to you, the explanation for this is the gradient is equal to 0. So I just kind of redrew the picture here. So what do we know about the gradient? The gradient has to be orthogonal to the contour. And so we say, oh, if the gradient is pointing in this direction here, or in this direction, well, that's orthogonal to this side of the contour, but it's not orthogonal to this side of the contour, and that's a problem. And ditto, if we try to draw, this or this here as to make it orthogonal to this part of the contour, now we're no longer orthogonal to this part of the contour. Really what's going on here is that let's think about the directional derivative of f at a here. It's the gradient f at a times u, where u is a direction vector. If we move along the contour like in this direction, we should get 0. If we move along the contour in this direction, the directional derivative should again give us 0 here. And the only way to accomplish that for both of those vectors is for the gradient itself to give us the 0 vector. Because the gradient gives us the 0 vector, the gradient of f is nothing more than the vector with the partial derivatives in it. And so this tells us partial f partial x is 0, partial f partial y is 0. Guess what? That's telling us that it's a critical point. And then how can we tell it's a saddle point? Well, here is 0. If we move off in this direction towards -4, we're going down. We're going down in here. If we go to the right instead, there's +4. We're going up over here. So slicing it in two different ways. Slicing in this direction, it looks like a local maximum. Slicing in this direction makes it look like a local minimum. So saddle point. Okay, now let's take a look here at directional derivatives here. So we're being asked for directional derivatives of f at points P and Q for both those vectors u pointing up and to the left. So first off, let's get a sense of the signs of the directional derivatives. So at point Q, f of q is equal to 4, f of p is also equal to 4, and moving in this direction makes things negative, makes things more negative. We're going from 4 down towards 0, the rate of change is negative, the directional derivative is negative. Let's write that down. And ditto for here, f of p is 4, here is 0, here is -4. Both of these directional derivatives are negative. But we're being asked to compare which one's bigger here. Well, the thing to notice is that the directional derivative of f at p is more negative, because as you're moving in this direction, you are decreasing more rapidly. Going from here to here, you drop from 4 to -4. Going from here to here, you drop from 4 to, let's say, 2 or something like that. So the rate of change is more negative here at P. And so we use that to conclude the directional derivative in the direction of u of f at P is smaller, more negative, than the directional derivative in the direction of u of f at q. So that is our final answer to part B here.